All right, guys. My name is Bryan Radmall, and today we're going to be talking about the photoelectric effect. So to understand this photoelectric effect, we first have to understand a concept developed by Albert Einstein. So we've talked about light in terms of rays. We've talked about light in terms of waves. Einstein had kind of this new idea, this new concept of light as a little packet of energy. He called this a photon. So a little packet of light or a little packet of energy. And each photon carries an energy proportional to the frequency of the light. So the energy of a given photon we can say is equal to hf, where h is equal to Planck's constant. Planck's constant, and this f represents the frequency of our light. So using the frequency, we can determine the energy in a given photon. So using this concept of photons, Einstein explained this photoelectric effect essentially by saying that when a photon strikes an electron, we'll say we have a metal plate here with an electron on it. When a photon comes and strikes that electron, the energy of the photon can eject or boot the electron off of that given material. But in order for the photon to kick off that electron, it needs to have enough energy. Without enough energy, it's just not going to work. So how much energy do we need to kick off this electron? Well, that's going to differ depending on what material we're working with. Every material has what we call a threshold frequency, or F naught. So F naught is equal to our threshold frequency, we can say. And so this determines how much energy that photon needs to have to kick an electron off of that material. If the frequency of our photon is less than the threshold frequency of that material, then when that given photon comes in and hits an electron, there's just not going to be enough energy there to kick off that electron. The electron's going to stay where it's happy on that material. But if the frequency of our photon is greater than that threshold frequency, then when this photon comes in and hits the electron, it has enough energy to boot it off, to kick it off. Now, if we change the intensity of our light in this first example, if we change the intensity, meaning that we send in more photons, it's not going to make a difference because only one photon is interacting with each electron at a given moment. So it doesn't matter how many photons we send in, there's just not enough energy in a photon to kick off that electron. But in our second example here, where the frequency is greater than the threshold frequency, it does make a difference if we change that intensity. So let's say we have another plate of metal here, and this plate of metal has multiple electrons. And so now we send in more than just one photon, or we increase our intensity. Now we can send in a few. So each of the photons we send in can interact with a different electron. So now we can kick off more electrons as we increase that intensity. Now obviously, as these electrons get kicked off, they have a velocity, they have a kinetic energy. And we can calculate the kinetic energy of a given electron as we kick it off using this equation. So the kinetic energy of our electron is equal to the energy of our photon minus the binding energy of that electron to its given material. So we already talked earlier about how we can find the energy of our photon. We said the energy of our photon is equal to Planck's constant times the frequency of that photon. And to calculate our binding energy, we can say that the binding energy is equal to, once again, Planck's constant, but now we're going to multiply it by that threshold frequency that we mentioned earlier. So now we can plug in those variables to our equation. So the kinetic energy of our electron is going to be equal to Planck's constant times the frequency of our photon minus Planck's constant times the threshold frequency. So if we have those variables, we can determine the kinetic energy of our electron. Now, this also just confirms what we talked about earlier, that if the frequency of our photon is less than this threshold frequency, then our kinetic energy is going to be negative. So clearly that electron is not going to leave the material. But if this frequency is greater than that threshold frequency, then the kinetic energy of our electron is going to be positive, meaning it's going to have a velocity. It's going to be ejected from that material. And so once we've calculated that kinetic energy of the electron, we know also that, switch back to our blue here. We know also that kinetic energy is equal to 1/2 mass times velocity squared. We know the mass of an electron. So once we've found our kinetic energy, we can use it to calculate the velocity of our electron that's been booted off. And that will be all for today on the photoelectric effect. Thanks for watching, guys.